So first things first here before we really get going, collision theory. All right, this has a basis in it's based on kinetic molecular theory. You guys remember kinetic molecular theory? KMT? You know, from like the gas law unit, we're talking about particle movement and all that sort of stuff, right? Because that's kind of what we're talking about again here. Right? We're talking about things, you know, having a reaction, reactants having a reaction and forming products, okay? And really what we're getting at here is we're trying to explain, right, why reactions occur. All right, so in order to do this, I'm going to give you a little demo here. In terms of, I'm gonna do a little beaker demo. I should say beakers on a string demo. That's really a much better description. All right, so I've got two beakers here, and I'm going to tape them to the string. So up here, I'm gonna there they are. Okay, so I got my beakers on a string over here. And yeah, okay. So I'm going to pull them. Hi. You're actually right there. Okay, I'm going to pull them a little bit apart. I'm going to pull them a little bit apart. Okay. We just had a collision, right? Anything happen? No, no. Beakers are still beakers, right? The beakers are still beakers. Nothing really happened. Okay. Nothing happened. Just a collision. Right? They collided together. Okay. My beakers. What are they representing here? What do my beakers represent? Yeah. Yeah. My particles are like. If I'm looking at a chemical reaction, what would they be? You're too small still. I'm just saying in general. Reactants. Yeah, that's all I'm looking for. It's just reactants, right? They're my particles that are reactants, right? These are my reactants. My beakers are reactants. But nothing happened, okay? Just want to make sure we're clear on this. Beakers equal reactants. All right, now, why didn't I get a reaction? Why didn't I get a reaction? Right, because I mean it's totally, and this might be something that I probably should put out there, is right. If we're having a chemical reaction, one thing that has to happen, right? If we've got, let's say we've got two things, and we got H2 and O2, and we want to make some water, right? Well, the hydrogen gas and oxygen gas have to collide, right, in order to have the reaction together. They have to collide. We have to have a collision, okay? That's the first thing that has to happen. Well, we had a collision between our reactants, but nothing happened. How come? See it? There was not enough energy. Great. Yeah, not enough energy. Right, not enough energy. Enough energy. We gotta have collisions with enough energy to have a reaction happen. I want to break these suckers. What are we doing? Right? Let's do this. All right, so I'm gonna pull them pretty far apart now. Okay. All right, we're hoping we get something to happen here. Oh yeah, all right. Right? There we go. Reaction. I want to talk. Get out of here. Hey, get out of here. I'm having reactions happening around here. And I know. You guys can come back to chemistry if you want. I know how physics is. Just come on back. Come on back. All right. So, sorry. All right. All right. We pull apart. We have a reaction happen. Yes. Okay. Reaction happens. Great. Okay. We had a collision with enough energy. All right, we had a collision with enough energy. Of course, that wasn't quite exactly what I wanted to happen. Okay. All right, we had a reaction happen. There was enough energy. Okay. What I was actually hoping for to happen was that the beakers would collide again. All right, but nothing would happen. Right, where they're hitting together with enough energy, but just nothing would quite happen. Because I was hoping that if I put them together in the right way, that when they collided, they would just kind of bounce off each other. You know, sometimes when you might drop a glass or like a beaker in the glass in the room or something, and you're like, oh, the phone, great example. Your phone's a great example of that. Sometimes you drop it, falls like on its face. You're like, no, right? And you go and you pick it up, and you're like, thank you, right? And it's fine, okay? But then there are other times where you like, and you like dropped it like that far, and you go and you pick it up and the whole thing is just shattered. Like, how did that happen? It fell like 2 inches, right? Okay? So energy plays a really important deal, but how the collisions happen too, like the orientation of your phone, like if it just hits on that like corner at like that perfect spot, and all of a sudden you pick it up and it's totally shattered, but you could throw it around. There's nothing wrong with it, right? Sometimes you slam it down on the ground, or you drop it totally by accident, and it falls like 5 feet, no problem, right? Okay, so. Right, the reaction happens if you got a collision, you got enough energy, but also the orientation is really important. Right, the orientation is important for the reactants, right? So, so you can think about your cell phone screen breaking. Great example. Okay. The cell phone screen breaking, right? So in order for a reaction to happen, because not all collisions, that's a great example of not all collisions are resulting in a reaction, right? Okay, I mean, look, if we had gasoline out, we spill gasoline, or you're carrying gasoline around in your car, right, all the time. There's oxygen in your gas tank. Okay, there's oxygen colliding with the gasoline all the time. Is the gasoline just like going up in flames? No, right? There's not just spontaneously. It doesn't spontaneously combust. Okay, when you had your little rockets, right? And you put the hydrogen gas in, the oxygen gas. It wasn't like all of a sudden you're holding it in your hand, all of a sudden, poof, it just shoots out of your hand, right? That would have been awesome if it worked that way. Okay, well, what you have to provide? Spark, the energy, right? The energy you got to provide. You get that sucker to explode. That's all it took was that little spark right there was enough energy to promote the collisions that were happening between the hydrogen and oxygen. I mean, your little pipette was filled with hydrogen and oxygen, right? But the reaction wasn't happening until you provided enough energy. Okay, so you got to have enough energy. You've got to have the right orientation in order for those reactions to happen. Okay, so collision theory here, to kind of sum it up, right? We've got kind of three things, right? You got to have collisions, right? You got to have collisions. I mean, that kind of goes without saying. It's collision theory, right? But I'm going to put it in there anyway, right? Second thing is you got to have collisions with enough energy. All right, and the kind of the third part of this, you got to have collisions with enough energy and the proper orientation. I'm off the screen there, so I'll circle that guy and bring it back over here. Right? So you've got to have collisions. You've got to have enough energy in those collisions, and it's got to be happening in the proper orientation. A great example of orientation and stuff is your body. Right? Is your body and stuff. Okay, your body does a great job of orienting molecules in the right way. Right? Because if you think about, we haven't gotten to this enough yet, but molecules and compounds, right? Ion compounds, covalent molecules, things like that, they have shapes, right? You saw that in biology. They have geometry, they have shapes, there's different bonding angles, all that sort of stuff, okay? Shape matters. And your body does a great job of positioning these molecules in just the right way that they'll fit together just like puzzle pieces and have a reaction happen, okay? What in your body does that? Not your DNA. Kind of further down the road, like if you go back far enough, your DNA would, yes, your DNA is important in creating these things, but these are the things that are doing the work, okay? Enzymes, bingo, right? The enzymes are there. The substrate comes in, our reactants dock with the enzyme or held by the enzyme in a particular way. We have the reaction happen, and it lets the products go, so on and so forth. So those enzymes are controlling the orientation to ensure that the collision happens in the right way, and you need just a tiny amount of energy then too. You got enough energy just in your 98 point whatever degrees Fahrenheit, right, of your body. That's providing enough energy for these reactions to happen. Okay. All right, so that's good stuff right there. Glass all in place here, right? Oh, cell phone, great example of orientation and energy, all that sort of stuff, right? Because sometimes you need just enough energy to make a reaction happen, and we'll talk about a little bit more like what exactly we call that in just a second. We're going to sweep up all the glass here. All right. This works great every time. Okay. Oh, that's kind of fun. Speaker caught some of that glass in it, but it's still good. Use this later. All right. Let's come back for more. Better get all this glass out of here before Mr. Weber told there somebody. Quite right. There we go. All right. Now we're good to go. More piece of glass right there. Okay. Yeah. Yes. All right. All right, so collisions with enough energy, and collisions with the right orientation. Okay. When we start thinking about this sort of stuff, there's particular things that we're going to get at that are going to affect like rates of reactions, because you can alter things about the reaction that are going to change, hey, maybe just purely the number of collisions that molecules have with one another. Okay, some percentage, like when you have a reaction, not all the collisions are resulting in a reaction, right? Because they have to meet these two other caveats, right? They got to apply with enough energy and the proper orientation. Some percentage of those reactions are, of those collisions are having a reaction. Well, how can you increase the number of collisions? Okay, think about how can you increase the amount of energy that's in those reactants in the molecules? Okay, and what is something that you can do to change the orientation to make sure that they're colliding with the right orientation? So we're going to look at, you guys are going to do a lab tomorrow and work through some of this and try to figure out what's going on with that. Okay, we'll change some different singular variable and see like, all right, well, what do you think's happening? What is changing? Is the amount of energy changing? Is the number of collisions changing? Is the orientation of these molecules changing? Like, what's really changing the rate of the reaction? Because when we start to get to equilibrium, we got to talk about rate. We have to talk about rate, how fast or how slow a reaction happens, how quickly equilibrium is reached, okay, and things like that. So, but we'll get to that in a second. Something I do want that kind of goes with this as well that we haven't talked about yet, and that is energy diagrams. All right, energy diagrams is kind of something that this goes with this to some extent, but it's something that we haven't done at all. Okay, so I want to make sure that we talk about energy diagrams a little bit. And something that ideally would have gone like in our heat unit way back then. Okay, but ultimately we'll just we'll draw a couple diagrams and we'll talk about them a little bit. So all an energy diagram is, it kind of just shows the potential energy of the reactants and products as a reaction occurs. Okay, so when we draw these, we have on the y-axis we got energy, and on the x-axis we have reaction progress, like how they're occurring, okay, as the reaction happens. So we're going to start off with some reactants, and you're going to end with some products. We'll kind of draw like this. There we go, something along those lines. All right, I'm going to label some different parts, and we'll kind of we'll go through and define these guys in 1 second. Bless you. So I want to put a couple different lines in here and draw kind of the level of the products, level of the reactants there. I'm going to say the reactants are like 10. This is at like, products are at 40, and the top of the top up there is at like 50. You know, it could be joules, whatever the unit is, it doesn't really matter. So it's kind of relative. Okay, just kind of relative, just kind of making some numbers up here. Okay, for this. Usually it's expressed in like joules or kilojoules. Okay, but so here's our reaction. We got some reactants. They end up with products at like around 40 as their average energy there, and we have the peak of our curve there at 50. Okay, so if we go from the top, oops, I want to change the color of that, red. If we go from the bottom to the top, okay, that amount of energy is called the EA, or that's the activation energy. All right, and that is the amount of energy necessary for the reaction to occur. All right, so that's the activation energy, or EA is kind of what it's abbreviated at. So for this reaction, what would the value of the EA be? Not 50, 40. Actually 40. We're going to need 40. Okay, all right, because you already start at 10. They have some energy there already. 40, if we provide 40 more joules or kilojoules or whatever, you're giving enough energy for the reaction to happen. Now, some have very large hills. Some have very small ones, right? In some cases, the energy of activation is really, really big. In other cases, it's really, really small. Okay, right? So you can a spark in your car is enough energy to combust gasoline, right? That's enough. It's a small energy of activation there to provide the energy for combustion. Okay. All right. So additionally, here we've got another thing on this graph that we want to be aware of, and that is the difference between the reactants to the products, and that is delta H. Okay, that is delta H. All right, delta H is called enthalpy. All right, enthalpy, and it's equal to the products minus reactants. And we'll get into more of this later. We haven't done a ton of this, but this is just kind of very in general. We'll come back to thermodynamics here in a little bit, a little more specifically. Okay, but enthalpy is what we're looking at here. So it's difference of the energy of the products minus the energy of the reactants. Okay, so if we were to calculate delta H here, yeah.
Is this diagram showing like how much, like how far into the reaction, like how much energy is being like spent, kind of?
Kind of.
So it's like that's like the total is how much energy was put into the reaction.
Well, enthalpy is just telling you, we're just kind of measuring things like as a reaction, as we go from reactants and you move to products, right? Because that's not a direct line, okay? Right? You just don't have products and then reactants. And I'm going to talk about this in just a second. You have reactants breaking down and forming into products, right? You have bonds breaking, bonds forming as you go from reactants, like H2O2, right? We have our two reactants. And when you did the rocket lab, right, you formed water as your product, right? So you have H2 bonds breaking, but you got the bonds between, and O2 bonds breaking, right? And then you have bonds forming between the H and the O, right? And that's what's happening here. You're transitioning from reactants to products as you go. Okay. All right. So we're just kind of representing it graphically or whatever. All right. So delta H for this reaction. So if we look at the amount of energy that the products have in relation to the reactants, what would be the kind of value here that we'd be looking at for delta H? Yep. 30. Is it positive or negative? Great. That's important, right? This is going to be a positive 30, okay, for this reaction. All right, this is going to be positive 30 for this one. Okay? So overall, the amount of energy that was in those atoms to start with, and the amount of energy that was in those things to end with, right? Reactants to products, increased, right? This is gained energy. Gained energy, right? This is an endothermic reaction. It's called endothermic. All right, it's endothermic. It's got a positive delta H. And that's really important. Endothermic, positive delta H. But gained energy from the surroundings in order for this to happen. All right. Reactions like this are going to feel cold. They're going to feel cold. Okay, so great example of this is when you go to the nurse's office or you hurt yourself a pee or something, and they bring you in there and then they pop that bag and they shake it up and mix chemicals together in the bag, and it's like an instant ice pack. Okay, that is an endothermic reaction. It feels cold because it's absorbing heat energy from the surroundings, and it's gaining energy. Okay, so it feels cold. Does that make sense? Okay, it's a tough one to understand. Remember, we've talked about heat flow, right? We've discussed heat flowing from one object to another. That's energy flow. That's what's happening here. Okay, the system here, the reaction gained energy from the surroundings. So energy increased in the reaction, right? So you feel it feels cold. It's endothermic, all right? Now there's a midway, so not necessarily midway is a bad word to describe it, but there's the transition between the reactants and products, and up here is said to be, that's the transition state. All right, at the top of the curve there. Okay, the transition state. So that's the transition from reactants to products. Okay, so you got bonds forming and bonds breaking. All right, you got bonds forming and bonds breaking there. Okay, that's the transition state, and that's where this kind of ball comes into play for today. Okay, this kind of represents the blue is reactants and the purple are products. The change as you're moving from one to the other is the transition state, right? It's transitioning between reactants, right, and products. Okay, that's essentially what's going on there, right? So if I have reactants, now I got products. Okay, so that's kind of what's happening there. It's the transition from one to the other. You've got to form some bonds and break some bonds. Not you got enough energy, you get over the hill, you can go from reactants to products. That's why. There it is. Okay, so the transition state between reactants and products, you got a little bit of both, right? You got some bonds forming, some bonds breaking, and you're somewhere in between the formation of the products and where you left at with the reactants, right? As you move from one to the other, you transition between the two. Okay, does that make sense? All right, that's kind of what we're looking at.
Oh my God.
Look alive! You're in the front row now. So you wanted that? You got it. All right. Sweet. There we go. All right. All right. So now this is endothermic, right? So there's obviously we can do the opposite of this too, right? Where heat's given off. Okay. So let's draw another energy diagram here. So I'm going to draw another energy diagram here with the opposite case happening. So that one there is endothermic, right? This one we're going to draw is exothermic. I'll do something like this. 10, 30, 50, right? We got energy on the Y, reaction progress on the X. And we'll start reactants, products. All right, so once again here we've got delta H. We've got our energy of activation. All right. So what is our energy of activation equal to for this particular graph, for this exothermic graph? 20. Yeah, just 20. All right. What about delta H? What is delta H equal to for this one? Products minus reactants. What's our enthalpy in this reaction? Careful. Products minus reactants. Bingo. All right, that's the key. All right, it's negative 20. That's important, right? The sign is really important, whether it's positive or negative. Okay, delta H has got to be positive or negative. Okay, this is exothermic, right? So that means energy is given off, right, or lost. Right, this is going to feel hot. It's going to feel hot. All right, so energy is lost from that reaction. So what's a good example of this? What's a good example of a reaction that's exothermic? Fire. Yeah, fire, right? Okay, that's a great example of exothermic. All right, a combustion reaction, exothermic. Hot, feels hot, it's giving off heat. Okay. Yeah, those are exothermic reactions. All right. Now there are different, it's losing heat to the surroundings, right? It's losing heat. Heat is flowing out, okay, from the reaction to the surroundings. So that's why it feels hot, okay? Exothermic reactions. Yeah, combustion, good example of exothermic reaction, right? All right, and just one other quick comment about the energy of activation. Right, that's the, we talked about, like, hey, that's the amount of energy for the reaction to occur. Like, that goes back to collision theory, right? Right, that's the amount of energy needed. Right, to get to the top of that transition state, to get up over the hill. Okay. All right, so there's a number of different things that are going to affect how, like, what's going on here and how we're going to do this. But ultimately, every reaction has some sort of activation energy. Okay. Some have more than others, right? Okay. All right, some have more than others. All right, so sometimes maybe you just need a spark for the reaction to happen, right? You need a spark. You gotta, right, when we had our H2 and O2 in our rockets, right, we had our spark, we had our launch mechanism here. You had to provide the spark, okay, in order for the reaction to occur, to get up over the transition state, to get up over the energy of activation, right? When you start a fire, the reactions that are going, that are combusting, are providing the energy to the other reactions that are having to continually have the fire, have the combustion reaction going, right? Sometimes the hill might be so small, it's just enough for the reaction to happen when the molecules collide with one another. Sometimes that's enough energy, okay? We've seen that as well, right? Mix two components together, mix two solutions together, they collide in the solution, boom, you got a precipitate, you got the reaction happened, okay? So that was enough energy for the reaction to happen. Other times you got to provide a lot more energy, okay? So that's kind of what leads us to equilibrium and things like that. But there are enough, there's a number of factors that are going to affect reaction rate. Well, first of all, I guess before I move on, are there any questions about endothermic and exothermic, like the difference between those two, okay, and the differences between like delta H and energy of activation or anything like that on a graph, in either graph there? Okay. All right, so factors that affect reaction rate. Basically, the question we got to ask is, what are some things that we can do to speed up reactions? All right, and this is where our lab is going to come into play for tomorrow, okay? So our lab tomorrow, so your reaction rate mini lab, you got mini labs going tomorrow, all right? I want you to come up with, tomorrow you're going to have to come up with 4 different things. All right, you're going to follow the different lab instructions there. And when you're done with it, I want you to be able to fill in these 4 different things and talk about, hey, what are things, like what that thing is and how it affects the rate of the reaction. Okay, so in terms of, you know, and we want to think about like collision theory, okay, right? We're talking about collisions, we're talking about energy of collisions, right? Number of collisions, energy of collisions. What else? Orientation, right? Right? You want to somehow figure out what's changing. What different things here are being changed by doing what you're doing to those different, well, while you go through the different scenarios in the lab tomorrow. Okay? So you're going to do a couple different labs, collect some data, take a look at, all right, well, because the experiments are kind of set up for you when you're affecting one variable. It's got decent experimental design, so you're affecting one variable, and you're going to see how that variable changes the rates of the reaction. We're going to just measure them in by time and things like that, and you'll just be able to observe them too. Okay? Right? And we're going to see what happens there. We'll come up with some different, there's 4 different factors. You might already have some ideas about what those different factors could be. Okay? I hope you do, because they somewhat kind of deal with stuff that we've already done. Like, you should have enough of an idea, all right, about some different things that can change the rate of reaction to make it go faster. Okay? All right, so that's kind of it. Tomorrow you're going to get a calendar and all that stuff, and you'll have a little problem set to work on that, and that's about it.